In today's lab, we're going to synthesize amyl acetate, which is an ester you can find in banana, in the oil of banana. So towards the end of the lab, it's going to smell like an over-ripened banana. You missed that. We're going to use the glassware in our micro kit. We need a short neck flask, a supporting rod with a connecting rubber piece, another connecting piece, an adapter, a test tube, a condenser, and a sleeve, and maybe a tiny stir bar. Put the stir bar in the round bottom flask. Connect the supporting rod. Connect the adapter. And this one is for the air condenser. And finally, put the sleeve and a test tube. Okay. So this is the apparatus we're going to use for today's lab. Okay, let's start adding our ingredients. We first need 1 pentanol into this round bottom flask. We need 2.7 ml of 1 pentanol. This is 0.7. Okay, this is 1 ml. We have exactly 2.7 ml of 1 pentanol. Okay, the next reactant is glacial acetic acid. We need 1.55 ml of glacial acetic acid. It is 1 ml. And change the pipette to 0.55 ml. Okay. We have our alcohol and carboxylic acid into our flask. This is a Fischer esterification. We need an acid to catalyze the reaction. Here is the concentrated sulfuric acid. We just need a catalytic amount of sulfuric acid, and it's not a good idea to open this here. I'm going to take this to the fume hood. Clamp your apparatus, tilt it to 45-degree angle, connect your round bottom flask, put the hot plate on a jack, place an aluminum heating block, and raise your hot plate to the round bottom flask. Okay, that's a complete setup for a reaction. I'm going to turn on the stirring and heating. Once it started boiling, we should turn on the timer. To monitor the temperature, I'm going to place a 220 thermometer on the heating block. The temperature is still at 60. 1 pentanol and acetic acid, they both boil above 100 C. So I'm going to raise the temperature and let's wait for the boiling. Okay, it started boiling at about 120 C. You can see that it's boiling right there, and the temperature, I don't know if it's is little below 130. I'm going to start the timer. Let it go for 45 minutes. What happens here is your alcohol and carboxylic acid react in a Fischer esterification, and the products are ester and water. Water is the byproduct, and at this temperature they both evaporate. Both the organic and aqueous component will evaporate, and they condense in the air condenser and drip back through the side arm into the test tube. So you have both the ester and water, the organic and aqueous phase, in the test tube. It's about 4 minutes now. I already got a few drops of organic, that is the top phase, and aqueous, the bottom phase. I don't want to lose the product, so I'm going to clamp this test tube. It's about 20 minutes. Half of the reaction mixture is now in the test tube. You can see the bottom aqueous layer and the top organic layer. Okay, that is 200 C. The temperature of the reaction is now a little below the 200. That is too much for this reaction. I guess I should lower the heating. Okay, it's almost 45 minutes. Our reaction should be complete by now. I'm going to turn off the heating and remove the product. I have the product in the test tube. It does smell like banana. I can't stand that, so let's put a baby stopper. The overall volume of the aqueous and organic is 3.6 ml, and the bottom aqueous layer is about 0.7 ml, 0.7 milliliter. This is what I obtained from the reaction flask. It's not the final product. It still has, or it may have, 2 protons on the oxygens. So it's just an intermediate. It's not the final product. I'm going to test the acidity of the organic phase using a blue litmus paper. I'm taking a drop of the top organic phase and dip it on a blue litmus paper. It turned red, which means it's still acidic. Now the question is, how would you neutralize this intermediate into the final product? Which base would you use? Sodium hydroxide or sodium bicarbonate to abstract the protons? You can answer this by assessing the basicity and nucleophilicity of the 2 compounds, sodium hydroxide and sodium bicarbonate. Sodium hydroxide is small, and the negative charge on the oxygen is not stabilized. So sodium hydroxide is a good base as well as a good nucleophile. Instead of abstracting the protons, the hydroxide can attack the acyl carbon, which is a nucleophilic attack. Instead of the reaction going forward, the reaction can go backward, so you get the acetic acid. Right. When you put the hydroxide on this acyl carbon, the alcohol will be gone, and what you get is an acetic acid, which is our reactant. So we don't want to use the strong base as well as nucleophile sodium hydroxide, we would use sodium bicarbonate. If you look at the structure of sodium bicarbonate, here's a central carbon, hydroxide, the double bonded oxygen, and the oxygen with a negative charge. This negative charge on the oxygen is resonance stabilized. Right, the negative charge can go make a pi bond. This pi bond can make a negative charge. So the negative charge is stabilized through resonance. It's not a strong base, and it's not a nucleophile because of the size of this. It's bulky. So sodium bicarbonate is what you want to use to abstract the two protons to get our product. Add your intermediate into the separating flask. Now add 10 ml of 5% sodium bicarbonate. Okay, that's a 10 ml of sodium bicarbonate. Here's the aqueous phase, and the top one is the organic phase. I'm going to mix the two liquids so the base will remove the protons from your intermediate. Let's clamp the separating flask and let the two phases separate. The top one is the organic phase and the bottom one is the aqueous. Let's drain the aqueous. Now I'm going to test the pH of this organic layer to see if I need more base. Take a pipette, take a drop of organic and put it on a blue litmus paper. Okay, it didn't turn red, which means the protons are gone. The organic layer is no longer acidic. That's what we want. We had enough base to remove the protons from the oxygen. Transferring the organic phase into a clean and dry polymer flask. Okay, so this organic phase may have some water drops because our physical separation may not be good. So we're going to do some chemical separation using the drying agent anhydrous sodium sulfate. Don't have to measure that. Take some amount of anhydrous sodium sulfate and put it into the organic phase. Okay. Give it a swirl and let it sit for 5 to 10 minutes. After about 10 minutes of drying, now transfer the liquid, the organic phase, from this flask into a clean, dry test tube. This is a different one, it's a new one. Okay, that's how much I could extract. The final volume of our product is about 1.3 mil, 1.3 milliliter. That is the ester amyl acetate, the banana oil. So we synthesized an artificial banana oil in our lab. It smells good. The next step is to do the IR spectroscopy and NMR spectroscopy.